next example on the Gauss. We have to evaluate the surface integral where the vector field given and the surface is surface of the upper 5 faces of the unit cube. Upper 5 faces. So let's sketch. What does it looks like? Upper 5 faces of the unit cube. Okay, unit cube. We have unit cube. And the value, they are all 1. So this is 1, this is 1, and this is 1. X, Y, and Z. Okay, upper 5 faces. So we know that for cube to be a solid, yeah, it should be this is a closed surface, right? But they don't asking for the whole surfaces, which is 6. If that, you can use the Gauss theorem, but this one you cannot use Gauss theorem because you don't have a solid. You only have the surface, all of the surface except the surface down here. Upper 5 faces, so except this plane. Okay. So you have this one, and you have the left wall, the right wall, the wall at the behind, and the wall in the front, and the top wall, but the bottom here nothing, so it is open. Okay, so in this case, if you want to use a direct method where you in order for you to obtain the surface integral, so your surface is the combination of surface 1, surface 2, surface 3, surface 4, and surface 5. So you have to provide the 5 double integral, where I think that one is very long procedure, right? Do you have any suggestion? Do you have any suggestion? What is the simple thing that you can do? Yes, you can firstly compute the solid, which is you have a closed surface. So then here you can use Gauss. I think I have mentioned this before. You can use the Gauss, which you consider the whole surfaces 6, and then you just subtract the surface integral for the whole, and subtract the surface where given by this one in blue. Okay, so given by this surface. Okay, so this surface. So for this you will save time, rather than you have to provide all the 5 and you compute for every single surfaces, find the function, and then evaluate the dot product, and then find the double integral and so on. So I think for me this one is more simpler, because this one you just use triple integral and find the divergent F. Find the divergent F, and this one. So in this case, you have to use a standard calculation. So let's say this one, I call this as a surface given by sigma 6. Sigma 6 is not part of the first 5 upper 5 faces. Okay, it's not. Sigma 6 is not part of the upper 5 faces. So you have to just compute the surface integral for the sigma 6. Yes, okay. So now, firstly, I want to compute the, let's say I call this A. I want to compute for A. So for that, we can, as we know that the surface integral for using Gauss, surface integral for the whole surfaces, sigma, can be represented or can be evaluated by using triple integral of the divergence of the vector field over the region, over the solid G. So for this, we have to find out the divergence of F. So for this, what is F given? F is given by xy, and then minus, okay, you have to be careful, you read, you don't just blindly copy them. So you have only I and J, so your y is 0. I also sometimes do the same mistake. Okay, so then again we have to be careful. Minus z squared. Okay, so finding the divergence, del x of xy plus 0 plus del z minus z square, then will give you y minus 2z. Okay, so then we can have y minus 2z dv. Okay, so by looking at your solid, you have a cube. So then, as usual, you have to give a name for what type of solid that we have. So let's say then you have to ignore, you have to consider that we have the total surfaces. This one is actually closed. This is our assumption, just to simplify our calculation, because we want to use a Gauss. So if I have that particular solid, then I should stay standing like that, where my sorry, this one's supposed to be, I want to have a standard orientation, so z, x, and y. So I have xy solid, where this is my region. So your dv is dz dA on over dxy or dy dx. So then what I can do here is y minus 2z dz, and then okay, now look at your region. So your region is a rectangle. Oops. Okay, so it is a rectangle on y-x plane, and we have 1, 1, no, 1, and then 1. So and that is your region. So now we know that we have a rectangular region, y minus 2z dz dx. So let's say I'm choosing dy dx dy. So x and y both limit 0 to 1. How about z? So z, lower bound is 0 and the upper bound also 0. Is 1. Okay, so then we evaluate the triple integral. So since the integration here is simple and your limit, they are all constant, because you can see from your sketching you have a cube, right? Cuboid. So meaning that all the limits should be constant and you will obtain negative half. Okay, so this is not so complicated. You can do yourself. I'm very sure that. So that's why I didn't show here. Okay, so next we are going to calculate the the second one, B. Okay, so now we compute for the second one, where you need to obtain the surface integral for this particular surface. So you have to determine what is the equation of the sigma 6. Okay. So the equation, if you look at from your sketching of the solid, so the equation here should be z equal to 0. Okay, so the equation of the sigma c here is z equal to 0, where z is a function of xy. Okay, so now to get the phi is z minus f xy, and this will give you z minus 0 equal to 0, so z equal to 0. So in this case, your phi is z. Okay, so next you're going to compute the gradient phi. So del x z, del y z, and del z z. 0, 0, 1. Okay, so now to determine, you want to get the n, whether n is positive grade phi or negative. Then you have to look at from your surface. But don't look at your surface here. You have to look at your surface in the solid given. Okay, so now you can see that your solid here, since we imagine there is a solid, this is not empty, this is a solid which is part of the cube. So you can see that when you see that n point outward, so it should be outward to the solid G. Okay, so your n is here in this direction. So it looks like it follows, the direction follows the z negative. Okay, so how can we know that? We have to just look at z or k, and look at the function of the sigma 6 here. So we have this one where z, so then you have to focus on k component, and from this one it is shown that n point to the k negative, this one. So you have to make sure that your k is negative. Is it negative? No. So meaning that you have to negative square root phi. So then we got 0, 0, minus 1. So that is your n. Okay, so then since we know that we can use the surface integral using f dot n dA region. Okay, so on xy plane. So now you have to find the f dot n. So just now our f is xy0 negative z square. So f dot n will be 0, 0 z square. Now vector. So 0, 0, 0 plus 0 plus z square. Alright. So then here we have z square, and now region. So your region is on xy plane. Now we have 1, 1, yx. So we have a rectangular region. So we have dx dy 0, 1, 0, 1. Then again, this is not so complicated to be differentiate. Okay, but before we okay, if you look at here, is that as we done for the surface integral before the Gauss? Okay, before I show you about Gauss. So is it possible to be directly integrate? Because remember, for surface integral, this information is very important. Okay, so from your function equation here, the equation of your sigma 6, so your region is xy, so meaning that to be your integrand, the possible integrand is only in terms of x and y, or xy. You cannot have z. So meaning that you have to replace the z here by the function of the surface. So so based on your function here, your z is equal to 0. So when you replace here, it just we can say that the divergence is 0. So remember I told you before, if your divergence 0, so your flux here will be 0, end up to be 0. Why? Because of you are integrating the definite integral. You have a limit. So then when you replace the limit, so when you integrate the 0, you get a constant. So when you substitute the limit of x and y, so it is not affected by the value of the lower bound and the upper bound, and then you will get a minus a. So a minus a, you will get, or whatever, constant minus constant, so you get 0. Okay, so meaning that as a conclusion, if your integral is 0 and you have a definite integral, whether you have triple or double or single integral, and you will end up 0. Only for the integral 0, not constant. Okay, 0. So so your result in B, you got 0. Result in A, just now you got negative half. So as a whole, the thing that we are looking for is the line integral, surface integral for the 5 surfaces. It's given by B minus A. The result in B, which is from Gauss, minus A. So B, you got negative half, A, you got 0. Then you got negative half. Okay, so this is the result of the surface integral for upper 5 faces of the unit cube. And you can see they give you the value of x, y, and z. Right.